Hello and welcome to our lecture on chapter 14 of the textbook, which is about sound. Sound is another example of a wave. So one of the ways that sound can be produced, it's a longitudinal wave, which means that it can be produced by a string uh, vibrating back and forth, and as the string vibrates one way to the right in this case, it compresses the it compresses the air right next to it, which means that it makes it so that the air right next to it is going to be tighter together, more uh, it's going to be more compressed, it's going to be more tighter together, held together with less space in between the molecules than on the other side, which is going to be rarefied, or it's going to undergo rarefaction, which is when there's less compression, there's less pressure, and there's less air between, or there's less air molecules in a given space. So you can kind of see why that happens, and that's what happens when you're talking about guitar strings or vocal cords, is that they just vibrate back and forth, and then as they vibrate one way, it causes, or as they vibrate one way to one side, it causes there to be a compression and rarefaction in the opposite side, which is going to uh, occur once every, these compressions are going to occur once every period of the vibration. So every time the vibrating string, the guitar string, the piano string, our voices, uh, our vocal cords vibrates, so it goes back and forth and back and forth. It's going to cause there to be a wave in the form of the pressure at a given distance away from the string. So what this happens is that how we're able to tell what's happening and what we're able to do is by uh, or do what we're able to do with regards to compression and rarefaction, and telling the difference between these pitches and wavelengths and all of the things that you're able to do as a human uh, is or as a person with working eardrums is going to be that we have uh, eardrums which feel the pressure at different points, and as it vibrates back and forth, you're able to your brain is able to decompose this into the sound into an information. It's able to decompose these pressure waves into information about what sound is coming from where, how loud it is, and what pitch it's at. So the speed of sound is one of those things that depends majorly on the properties of the medium and doesn't depend on the frequency or the wavelength of the speed that's going for there. For the most part, at least for introductory physics, it doesn't depend on the frequency. But the speed of sound is generally dependent only on the properties of the medium. So at gases at 0 degrees Celsius, you have a velocity of 331 meters per second through air, 316 through oxygen, 259 for carbon dioxide, and then 965 for helium, and 1290 meters per second for hydrogen. So that's a significantly higher speed of sound for hydrogen and helium than it is for just regular air. And then ethanol also has speeds of sound somewhere in the or not ethanol, liquids at 20 degrees Celsius also tend to have velocities of around 1500 or 1400. But solids have the widest variety out there in this table, going from 54 meters per second for vulcanized rubber, which is significantly lower than the speed of sound in air, to 5960 for steel, which is going to be much, much bigger than any of the liquids, any of the gases. It's just going to be a much bigger range dependent on the chemical properties, dependent on the properties of the system. And then how we and then V is equal to F times lambda, where F is the frequency, which is measured in hertz, and lambda is the wavelength, which is measured in meters. So frequency is, as we went over in a previous lecture, frequency is how many times the pattern will repeat in a given time period. So it's how many times the pattern repeats in, say, 1 second, which could be, if it repeats 2,000 times in 1 second, then that means that has a frequency of 2,000 hertz, Hertz. And then the wavelength is just how long it takes to repeat in space. So sound intensity is what we generally describe when we're talking about sound, which is equal to the power divided by area. And this power divided by area, instead of pressure divided by area or anything like that, is just because the intensity, which is this I, is given by how much energy is output over a given time, which is the power, which, if you'll remember, power is work over time, divided by the area that it has to travel, so the surface area that it has to travel. So when you have a small surface area, then that's going to be a very small amount of the power that's going into messing with your eardrums and hearing, but that's also going to or of the total power that's going to be going into your eardrums and hearing, but it's still enough that you're able to make out the intensity based on how sensitive our ears are. And then you also have beta, that form in units of decibels is equal to 10 log base 10 of intensity over an initial intensity. So this intensity level, these decibels, are like, so I naught is the lowest intensity that we are capable of hearing, and it's about 10 to the negative 12 watts per meter squared. And the sound intensity is logarithmic, which means that sound with 10 times more decibels is 10 times as loud. So if you have 10 decibels versus 0 decibels, then it's going to be 10 times louder than the 0 decibels. But if you have 20 decibels versus 0 decibels, then it's going to be 100 times louder than the 0 decibels. And then if you have 90 decibels versus 50 decibels, then 90 decibels is 10 times 10 times 10 times 10, so 10 to the 4th times louder than the 50 decibels is, because it has a difference of 10 times, or it has a difference of 10 decibels for every 10 times the scale. So it's kind of like an earthquake scale. If you know those scales, where an 5.0 earthquake is 10 times has 10 times the energy and 10 times the intensity as a 4.0 earthquake. So it's just one of those types of scales, which is called a logarithmic scale. And then just to be complete, basically, I included a drawing of the ear, and then the ear canal, the inner ear, and the middle ear, which just shows how we are able to hear. There's the eardrum that's vibrating back and forth and causing there to be signals in our ears that are transferred to our brains, which are then decoded into information about the sounds around us. So humans can normally hear frequencies from about 20 to 20,000 hertz, but other animals have different ranges. So dogs can hear sounds as 450,000 hertz, and bats and dolphins can hear up to 110,000 hertz. And then sounds below 20 hertz are called infrasounds, whereas above 20,000 hertz is called ultrasound. So if you've had an ultrasound in your life, then that's just because it's at a higher frequency than the sounds that humans are capable of hearing. That's why it's called ultra or higher sound. And then the perception of frequency is called pitch, and the perception of intensity is called loudness. So that's basically how we interpret sound. That's very not even technological, that's just biological, mostly, or it's as biological as it is physical. But this Doppler effect is just a physical phenomenon that doesn't really have to do with uh, it doesn't really have to do with a anything to do with your biology. It only has to do with the sounds that you're apparently going to hear. So if you look on the top right picture here, you'll see a car that is driving from left to right, from X to Y, that is emitting sound. And then you'll also see that because it's emitting sound at the same time as it's moving forward, each of the circles for the sound it's emitting are going to be moving to the right, from left to right, at the same speed as the car. And then these circles, because they're moving from left to right instead of the initial center of one circle, if you look on the right side, it looks like the distance between the circles is a lot shorter than the distance between the circles on the left side. So this is called the Doppler effect, where the apparent frequency, the frequency or the pitch that you hear, is going to be changed based on what the apparent wavelength is going to be. So the apparent wavelength goes down as the car approaches you, and goes up as the car is away from you, which means that you're going to observe a different frequency for if the car is coming towards or away from you. So F observed is equal to the velocity of the wave, F, the initial frequency times velocity of the wave, over the velocity of the wave minus or plus the velocity of the source. So the velocity of the source is what's coming towards or away from you. So if you have a higher, if you're going, if it's coming towards you, then this is going to be VW minus VS in the denominator, which means that the observed frequency is going to get higher, and if it's going away from you, then it's VW plus VS on the denominator, which means that the observed frequency is going to get lower because the denominator is getting bigger. So this also is true if the observer is moving towards or away from a sound. In this case, it's F observed equals Fs, the frequency of the source, times velocity of the wave plus or minus velocity of the object or of the observer divided by the velocity of the wave. So in this case, if the observer is moving towards you, the sound, then it's going to have a higher frequency for the same argument as before. And if they're moving away from the sound, it's going to have a lower frequency by the same argument as before. And then in addition to this, there's also the sonic boom, which occurs as a moving source exceeds the speed of sound. And then the last thing that we're really going to get into while we're talking about sound is resonance. So resonance is when a driving force puts energy to a system at a certain frequency, which is not necessarily the same as the natural frequency of the system. Over time, the energy dissipates and the amplitude gradually reduces to zero, which is called damping. The natural frequency is the frequency at which a system would oscillate if there were no driving and no damping force. The phenomenon of driving a system with a frequency equal to its natural frequency is called resonance, and resonance, and a system being driven at its natural frequency is said to resonate. So basically, if you're driving a system with your voice or a tuning fork or anything like that, so you're just driving the system with something that releases waves at a certain frequency, it's going to cause the waves to rebound around the system, which is going to cause damping. So damping is when the system just energy is lost, so the sound of the system just gradually decreases. But there is also a certain resonance frequency, which is based on the materials of the properties of the material and the geometry of the material, which if you drive it with that same resonance, instead of damping, it builds on top of each other. So it creates a resonance, and by doing this, by singing at a certain resonance, by singing at the resonant frequency, you can get a glass object or a glass of water to resonate and then eventually shatter, because the energy that you're putting in is not going to dissipate in the same way that it does for off resonance frequencies. So this is also there's also something called a beat frequency, which if you have slightly different frequencies, then they're going to then as you see here, you have two pure waves, you have two waves that are just sine waves, and they're slightly different frequencies. So when you add them up, at some points it's going to be destructive, at some points it's going to be constructive over time. And the distance between two of these destructive periods or these constructive periods, either or, is going to be a new frequency, which is given by the absolute value of the difference between the two frequencies. So that's just the thing that happens. It's a thing that happens when you mix two different waves with different wavelengths together, which is something that's going to happen if you're dealing with electronics or sound or anything like that. So it's not immediately obvious what the purpose of this is, or like what the uh, practical purposes of this could be, but it is something that you need to watch out for if you're trying to do anything with waves. And then the final thing is that these resonances that we were talking about earlier are they are properties of the material and the number of wavelengths that can fit in the material. So for example, here we have one end of a tube closed off and one end open. So the resonant frequency is 1/4 of so it has the boundary conditions that at one end it has to be a node, at the other end it has to be an antinode. So if that's true, then there's only a certain amount of wavelengths that are allowed. The longest wavelength that's allowed is going to be the fundamental frequency. And then from there, you get overtones, which are other wavelengths that are allowed and are going to create resonance. So the first overtone is one where you have 3/4 of the wavelength. Earlier, you had 1/4 of the wavelength. For the second overturn tone, you have 5/4 of the wavelength. For the third overtone, you have 7/4 of the wavelength. So this wavelength is dependent on the material properties, but this is how flutes work. Flutes and clarinets and objects like that, where you have these certain, you just blow into the flute and you have these certain frequencies that are going to resonate, and that's the sound that's going to come off. It's going to create resonance with regards to your system, and that's the sound that's going to be noticeable when you're play the flute. You get this like very clear sound from just the air that you're blowing in resonating at these frequencies. And then for the last part, I'm just going to say that there are other types of stick or other types of objects that don't have this closed end. So you can either have what we see here, where both ends are open, which means that both ends have to be antinodes, which gives you a fundamental of lambda equals 2L. First overtone of lambda equals L, second overtone of lambda equals 2/3 L, and third overtone of lambda equals 1/2 L, where L is the length of the pipe. Or you can have the opposite, which isn't, or which unfortunately isn't demonstrated here, which you get for piano keys or guitar strings. So piano strings or guitar strings where the both sides have to be nodes instead of antinodes, but you're going to get the same behavior or for the same number of allowed wavelengths as for an antinode as you are going to get for a node. So that's going to be my presentation for sound. I hope you enjoyed it. If you have any questions, feel free to reach out to me. Thank you very much.